Alright, let's take a look at some derivative rules. So we stated that the derivative is basically the instantaneous rate of change function to a point of x. It's also the slope of the tangent function, right, to a point of x. And there are a few rules that govern derivatives. I've kind of summarized the four major rules outlined in this video. So the first rule we're going to be looking at is a constant rule, where f of x is equal to some kind of constant. Then we're going to be looking at the power rule, which is really common for polynomials, right? Then we're going to also take a look at the constant multiple rule, right, where f of x is equal to some constant times a function. And then we're also going to take a look at the sum and difference rule, which I kind of collectively expressed it because it's really the same notion, where h of x or some kind of function can be written as two or more different functions. Okay, so let's take a look at the constant rule, and I'm going to be doing examples for each of these rules. And when we're looking at the derivatives, we're going to be using these two types of notations. We're going to be looking at the Lagrange notation, which looks at the derivative as using the symbol prime, right? So the first derivative of a function f of x is f prime of x. The second derivative is f double prime of x, and so forth. We can also take a look at this in terms of Leibniz's notation, which basically expresses the derivative as the rate of change of y with respect to x, right? And the d represents a small incremental change, right? I like the Leibniz's notation because of the modifier, the derivative modifier dx, right? It just means to take the derivative of something with respect to x or whatever the denominator's value is, okay? So what I'm going to do is I'm going to do an example for each of them. Let's start with the constant rule. So using the constant rule, f of x is equal to a constant. Let's say f of x is equal to 5. Okay. Using Lagrange's theory, the derivative function f prime of x is equal to the derivative of that constant. I'm going to use Leibniz's notation, the the modifier ddx of 5, or the rate of change of 5 with respect to x, and the rate of change of any constant is 0. Okay? And the reason for that is because when we have a constant on a graph, like for instance, if this is 5, this is y is equal to 5, the slope of the tangent at any point on this graph is going to be 0. Okay? Take a look at the power rule. So let's say f of x is equal to 2x to the power 2. Okay? The derivative, f prime of x, is basically the power n times a, which is 2 times 2, which is 4, x, and then we subtract 1 to the power. So this is 4x to the power 1. We don't have to write the 1. Okay, and you can see the same thing being written in Leibniz's notation. I'm just kind of incorporating the two together, right? But I do like this modifier, the derivative modifier that is incorporated by Leibniz's notation, because it shows you exactly what to do, what you're doing, right? So it's a good way to just kind of show your steps. Let's take a look at the constant multiple rule, where f of x is equal to some kind of constant times g of x. When you're doing the derivative, you can actually write the constant on the outside. So this is kind of exemplified using Leibniz's notation. You can see that the constant is kind of taken away, and then you can do the derivative of the inside, right? So in this sense, let's say we have f of x is equal to 5x to the power 4, right? F prime of x is basically equal to 5 times the derivative of x to the power 4, which is 5 times, and I'm going to use power rule again, 4x cubed, which is basically 20x cubed. Okay, so it's kind of similar to the previous example, right? It just tells us that we can take the constant out and then do the derivative of the function by itself. The last rule here is the sum and difference rule, right? Where if h of x is made up of two or more different terms, right? The derivative is the derivative of all the terms, right? And in this case, let's do h of x is equal to negative 3x squared minus 4x. Then h prime of x is equal to the individual derivatives of each. So the derivative of negative 3x squared minus the derivative of 4x. And then if you employ the power rule, you get negative 6x minus 4. Okay? Yeah, those are some of the derivative rules which we're going to be using to do questions in the future.